Welcome to Module 5. This week we will be talking about simple linear regression. This is the first time you will be introduced to the concepts of predictive analytics. So we will use data sets to create predictive models. We will predict a variable using other variables. So this is a good example to start with. So here we have the house price plotted against house size, and this is a scatter plot, so you can see that there are these dots showing different data points, and you'll see that there is a line that tries to identify the relationship between the price and the size. Price is what we call the dependent variable, and size of the home is the independent variable. So the price is determined by the size of the home. And as we expect, when the size of the home in square feet increases, we expect that the price will increase as well. Now, a lot of times when we are studying these relationships, the data will not follow a straight line. There will always be some variation in the data set. And so the idea of simple linear regression is to plot a best fit line that best represents the data. And so we see here that this line, this blue line, tends to be the best representation of the data that is given here. I have with me Professor Wan. So Professor Wan, what is a response variable? And what is a predictor variable?
So the response variable will be in your y-axis because that is the variable that responds to the changes in this case, the size of the home. That is also called the predictor variable. It's the independent variable because it does not depend on the behavior of any other variable. However, the response variable is equivalent to the dependent variable because that depends on the independent variable or the size of the home.
So the predictor variable is what is used to predict the response variable. The dependent variable is just another way of calling out the response variable, and the independent variable is just another form of the predictor variable. So in general, in this lecture, we will be discussing all regression models in terms of dependent variable and independent variable. So the example that we just saw, the price of the home was the dependent variable because it depended on the size of the home, which was the independent variable. As we saw in the first example, a simple linear regression line will be a straight line, as we know that the straight line can be represented in this form. This is the form of a simple linear regression line, where we call E expected value of y. Y is the dependent variable, equals beta 0 plus beta 1 x, where x is the independent variable. Beta 0 and beta 1 are parameters that we will estimate using sample data. And these parameters will determine the slope of the line and at what point the line crosses the y-axis. Professor Wan, we can see that this is the simple linear regression function, but this also reminds us of another equation that a lot of students have probably seen before, and that equation is the equation of a straight line.
In this case, b sub 0 represents the y-intercept. That would be where the straight line crosses the y-axis. So that particular value is the y-intercept in this equation is represented as b sub 0. B sub 1 is the slope of the straight line, how steep going up or going down that line represents. So that will be the equivalent in simple terms of the y rise over the x difference. So the relationship, it establishes the relationship between how much the y increases as a function of x.
That is correct. So if we recall, y equals mx plus c was the equation for the straight line. And in that equation, m was the slope, and c used to be the y-intercept. Well, in this case, beta 0 is the y-intercept, and beta 1 is the slope. The reason we don't use y equals mx plus c representation here is because this serves a different purpose. We're using the straight line equation in terms of a regression function, where we will use values of x, or independent variable, to predict values of y, or dependent variable. The concept of regression equation is quite simple, and the idea is to minimize the absolute error of predictions. And so how do we do that? Well, this participation activity 6.1.7 does a good job of displaying that. So here are 4 data points. So they're given right here as well. If we have a line that is parallel to x-axis, then we can calculate the error between the actual data point and the predicted point. For example, note that in this case, the actual point happens to be at 5. And the point that is on the line for the same value of x is at around 17. And so the error, which is displayed here, is the actual point, which is 5, minus the predicted point, which is 17. And so the error is negative 12. Same is the case here. For x equal to 3, the actual point is 5. The predicted is, again, 17, and so the error is negative 12. For this point where x is 7, the actual point is about 27, and the predicted again is 17, and so the error is 10, and so on. So we see that these are the error terms. Now if we move forward, if we instead of having a line that was parallel to x-axis, if we have a line that is slightly slanted, then you'll see that the error will decrease a little bit than before. If we keep doing this, the error will keep decreasing. And you notice that at one point, if the line keeps getting steeper, then the error will start going back up. So at some point, we have minimized the absolute error. And that is the idea of regression equation, where we try to minimize this error between the actual data points and the predicted data points. For regression equation, we will not use absolute error. So we will not be using the sum of absolute error, trying to minimize that. We will use sum of squared errors. And we call this the method of least squares, again, which is how we minimize the sum of squared errors. Here's the equation that we're going to use. So this is, although it looks a little bit daunting, it's very simple. You'll notice that beta 0 minus beta 1 xi, this part is the form of the regression equation. And what we're really doing here is we're taking the actual data point represented by y sub I. This is the actual value of dependent variable in the data set, and we're subtracting the predicted value from the regression equation. And so again, this is just the error. And then we're squaring the error, and then we're summing all of these errors for different values, just like you saw in the example above. And so the idea again is to minimize this sum of squared errors. Before we can create regression models, there are some assumptions about the model that we need to discuss. And this is also something that should be tested for all the models that we create. So here are some assumptions. Error term must have a mean of 0. Error term has constant variance, and the error term should follow a normal distribution.
So in this particular case, looking at the assumption of having a mean of 0 on the graph on the left, we're looking at the residuals, which is nothing more than the errors, and you see that the same number of mean values are distributed above 0 as well as below 0. So in this particular case, that requirement is satisfied. However, if you look at the graph on the right, the residuals, the error terms, are all grouped at the bottom. So in that particular case, the mean value is not 0. So once again, the graph on the left satisfies the requirement of the mean equals to 0 because it has an even distribution.
The second assumption was of constant variance. So again, you can use a graph, a plot of residuals against the values of independent variable. So in this case, you can see that the error terms for increasing values of the independent variable, they tend to sort of be evenly distributed again. However, in this case, you will see that the error terms are not evenly distributed for all values of the independent variable. So you'll notice a trend where for increasing values of independent variable, the error terms tend to inflate, meaning that for smaller values of the independent variable, the errors are small, but as the independent variable increases, so do the errors. So this is a case where the assumption of constant variance is violated. Again, if you were to create a regression model where you'll get an equation, you can even use it to do predictions, but then when you plot residuals against the independent variables and you see something like this, again, you should be wary of that model.
In the case of normality, we have that the graph on the left, you see that all the variations, the sample quantiles are gathered along the straight line, which means that the distribution is approximating a normal distribution. However, the graph on the right shows the opposite. You see that the sample quantiles deviate from the straight line. So in this particular case, the normal distribution is not being followed. And as Professor Quadri said before, if you look at the x-axis, you see that as the quantiles increase, the deviation is larger instead of following the straight line.
Note, however, that this is the sample quantiles and not the residual itself. So this plot is often called a QQ plot. And in Python, you can get this plot where you can see that the normal probability line is given here. In the left case, the error terms are normally distributed because they follow the normal probability line. In the case on the right, the deviation from the line causes a violation of the normality assumption. Another assumption that we need to be sure is one where we're assessing the independence of data a long time. So here, note here that you have a patterned residuals. And here the residuals are again sort of evenly distributed. Whenever you see patterns like this, the independence assumption is violated. So when you create your models and you plot residuals against your independent variable, if you see any pattern in your residuals, then the independence assumption is violated. So we recall from the regression model that we use the independent variable to predict the dependent variable. And we looked at a few examples for data points on a graph, and we noted that there was some kind of a relationship between the dependent and the independent variable. And then we plotted a straight line to best represent that relationship. Now, how do we measure that relationship? So we can use concepts of correlation to measure the relationship between a dependent and an independent variable. So here is an example. Normally what we say is that we have a positive correlation between two variables. When one variable increases, the other increases as well. And then in the other case, we have a negative correlation when one variable increases, but the other one decreases. When you perform correlation and you calculate the measure for correlation, you will get a number that will be between -1 and +1. If you were to calculate the absolute value of correlation, here R represents the correlation coefficient or the value of correlation. If that value falls between the absolute value falls between 0 and 0.4, then you have what we call a weak correlation. When that value falls between 0.4 and 0.8, then you have a moderate correlation. And when the value is between 0.8 and 1, then you have a strong correlation. And when the value is 1, you'll notice that all of the data points between the two variables will fall exactly on the straight line. Now note here that we are using the absolute value. So you also have a strong correlation when you have the correlation coefficient between -0.8 and -1. Moderate when it's between -0.4 and -0.8. And weak when it's between 0 and -4.
Let's take a look at a graphical representation of what Professor Kadri just described. If you look at graph A, it is a straight line. There is basically no errors between the two variables. So they are both they are very highly correlated. If you look at graph B, you notice that the error size increases. So the correlation in that example will be a moderate positive correlation or weak. And then in the case of C, is a very weak correlation because all the points are widely spread apart.
And similarly in D, you'll notice that again we have a perfect correlation. All the data points are pretty much following a line, although in this case you have a negative correlation because as the value of one variable in this direction increases, the value of the dependent variable here, you'll notice, is decreasing. So one is increasing, the other is decreasing, so we have a negative correlation. Again, in this case, we have a negative correlation, although it's moderate because now the points are, they tend to lie not on a straight line, they tend to vary a little bit. And in the last case, you still have a negative correlation, however, the points are sort of spread out. So you have negative correlation, but it's weak. So we can also perform a hypothesis test for the correlation coefficient that we calculate. The hypothesis test will tell us whether the correlation coefficient is significantly different than 0 or not, we will have a null hypothesis where we can say that the correlation coefficient equals 0, and we can have the alternative hypothesis as being one of this case. So for example, let's say that in a particular problem, we come up with a correlation coefficient of plus 0.7. Well, in that case, we can either pick the alternative hypothesis as correlation coefficient not equal to 0, or we can pick correlation coefficient is greater than 0. So if we were to pick that, then we can use the test statistic that is calculated as this. This gives us the t statistic that is based on the t distribution, and the rest of the steps are the same. We calculate the p-value, and then we compare it against alpha, which usually is 0.05 or 0.01. And if the p-value is less than alpha, we reject the null hypothesis. And if the p-value is greater than alpha, then we do not reject the null hypothesis.
One last point that I would like to make is that correlation does not necessarily say that there is a causal relationship. In other words, if two variables are correlated, you need to also establish whether one variable is the cause of the other one. And this is important to keep in mind because, as you've seen it in, for example, in politics or the press, sometimes the implications are that a particular event is correlated with another event. However, just because the other event happened, it doesn't necessarily mean that it caused the other one. So, for example, in the case of smoking, is smoking really related to lung cancer? And you might remember that we went many years, the company saying that it was correlated, but it necessarily was not the cause of lung cancer.
For regression equations, we also have coefficient of determination. And so as it says here, the coefficient of determination that is denoted R square gives the ratio of the variance in the response variable explained by the predictor variable. Note that the representation for coefficient of determination is R square, and it literally is R square. It's just the square of the correlation coefficient. So once you calculate your correlation coefficient, you can square it to get the coefficient of determination. In the case of correlation, in which we had a quantitative measure of the relationship between two variables, the coefficient of determination, on the other hand, is telling us how much of the variation in the response variable is being predicted by the model that uses all of the independent variables. And ideally, we want that ratio, that percentage, to be high. So for example, you may get a value of, say, 30%. And what that means is that only 30% of the variation in your response variable is being predicted by the model using the independent variables. Or you may get an answer that is 85% of the variation is explained by the model using the independent variables. Let's now do an example of correlation in Python. So here we have the dataset being imported from a file called examscores.csv. This file has data on exam scores for 4 exams. And we're going to calculate the correlation coefficient between exam 1 and exam 4. And what that means is we're getting a quantitative measure of any relationship that exists between exam 1 and exam 4. So let's print this. We're going to use the Pearson R, which is a method in scipy.stats submodule. Pearson R is a correlation coefficient. And we will calculate that, and then we will print it. So as you can see here, when you print it, you get two numbers. And again, this is not confidence intervals. The first number represents the correlation coefficient. This is the correlation coefficient value. And the second number here represents the p-value if you were to do a hypothesis test for correlation coefficient. And so the correlation coefficient is 0.26. And recall that the null hypothesis for testing the correlation coefficient is that the correlation coefficient equals 0. And for the alternative hypothesis, we can pick that the correlation coefficient is greater than 0. So because we're getting a p-value of 0.06, we note that if we were to use alpha as 0.05, then the p-value is greater than alpha. And therefore, we will be unable to reject the null hypothesis. So we will have to assume that the correlation coefficient in this case is 0. But Professor Wan, we note that first of all, we have a positive value, so it's plus 0.26. Plus means that the correlation between exam 1 and exam 4 is positive. So as the scores for exam 1 increase, the scores for exam 4 increase. But what can you say about the relationship? Is it weak? Is it moderate? Or is it high?
In this particular case, it's weak. You can see that the value of 0.06 compared to 0.05 is fairly close. So it's a marginal relationship, and you have to be careful with the assumptions that you will make concerning this model.
Now we can run a regression model for exam 4 using exam 1. And what that means is that exam 4 is going to be our dependent variable and exam 1 is going to be our independent variable. Now in general, when your correlation coefficient is small and so there is weak relationship between two variables, is generally not recommended that you run a regression model. But we will see, this is just an example, and so we will see how the output looks and how some of the stats that we've been studying, how do they look when they print. So we can use the OLS method in statsmodels.formula.api submodule. It takes as input an expression like this, where exam 4 is your dependent variable. It's written first, and then you have the tilde sign, and then you have all of your independent variables next to it. So in this case, we only have one independent variable, so we're going to just type that. And then we will use the method .fit to show the results, and then we will print the summary of those results as given here. So let's do that. Here are the regression results. So note that it prints what was the dependent variable. So it prints the name of the dependent variable. It tells you that the method is of least squares. So we have 50 observations. Here, note that we have our R squared as 0.068. So remember, we wanted this value to be high. We want a lot of the variation in the dependent variable to be predicted by the model using the independent variable. Well, in this case, we only have 6.8% of the variation in the dependent variable getting explained by the model that uses the independent variable exam 1. And that's very low. So just like we explained before, because the correlation coefficient is so low, there's not really a good relationship between exam 4 and exam 1. That's translating into a model where we are unable to explain most of the variation in the dependent variable. So Professor Wan, looking at this output, if we had to create a regression model, what would be the values for parameters beta 0 and beta 1?
In this particular case, the intercept or the y-intercept is 57.76 as stated in the model, and then the slope for exam 1 will be 0.23 if we round it up to 2 decimal places.
That is correct. So if we were to write the relationship, it would be exam 4 equals 57.7627 plus 0.2266 exam 1. This is how you would write this regression model. 57.7627 is the intercept, and that is given here, and 0.2266 is the slope, that is the coefficient of the independent variable exam 1, that's given right here. So the first column here will give you the coefficients for your regression equation. Correlation, that equals 0.2613, and coefficient of determination, that equaled only 0.068. In almost all of the regression models, there will be a step where you will have to interpret the values of B0 and B1, beta 0, beta 1. And the idea behind that is to be able to explain what those numbers mean. So we recall that beta 0 is the y-intercept. That is the value of y when the independent variable has a value of 0. And so what this represents is what would be under the model, what would be the value for the dependent variable when the independent variable gets a value of 0. Now in a lot of cases, this will have no practical meaning. Recall the example where we were predicting the price of homes based on their square feet area. We used a regression model in which the dependent variable was price and the independent variable was square feet area. The value of B0 in that case does not make practical sense because a house cannot have an area of 0 and also have some price. And so although you will get a value for your beta 0 estimate, but that value will not have a practical meaning. In other cases, there may be a practical meaning for that value, so just be careful when you do your interpretation for beta 0. Now beta 1 on the other hand is the slope. That is the coefficient that goes next to the independent variable. So what does that represent? Well, we know it represents a unit change in independent variable, how much change that causes in the dependent variable. In this example here, note we have beta 1 estimate as 0.2266. And what that means is for each unit increase in exam 1 score, exam 4 score will increase by 0.2266. So for example, if someone scores 70 for exam 1, then we can plug in 70 here and get the value for exam 4. And now let's say somebody scores 71. That's just one more point than the previous score. That 1 unit increase in exam 1 will give you an answer that is going to be 0.2266 more than the answer when exam 1 was 70. The next section talks about testing the simple linear regression parameters. So when we get our estimates for beta 0 and beta 1, the next step is also, after we have sort of done its interpretation, we also need to make sure that they're statistically significant. And so we have to perform hypothesis tests. In general, we look at the slope parameter or the estimate for beta 1 and we do its hypothesis test. The steps for the hypothesis test are going to be just like what you've seen before. The test is going to be a t-test. The null hypothesis will be that beta 1 equals 0, and the alternative hypothesis will be that beta 1 is not equal to 0. We will use Python to get our test statistic and the corresponding p-value. And once we have our p-value, we will just compare it to alpha. Alpha is generally going to be 0.05. And if the p-value is less than alpha, we will reject the null hypothesis here. Otherwise, we will not reject the null hypothesis. So note that if we do not reject the null hypothesis, we're essentially saying that beta 1 parameter has a value of 0. If the beta 1 parameter has a value of 0, then the regression model will just be that y equals the intercept, because beta 1 is 0, so the term for the independent variable will just go to 0. Going back to the example that we just did, we noted that it printed the coefficients for intercept and the coefficient for the independent variable exam1, the standard error, but then the next one is the t statistic, the test statistic, that's 1.876. And then the probability, the p-value of 0.067. And this is a two-sided p-value. And recall that the alternative hypothesis was that estimate for beta 1 is not equal to 0. So that's a two-sided test. This returns a two-sided p-value. So there's no need to divide by 2 in this case at all. You just take the p-value, you compare it to your alpha. So if the alpha is 0.05, our p-value is 0.067, that's greater than alpha. So we will not be able to reject the null hypothesis. And because we cannot reject that, essentially this value here, we will have to say that it's not significant. So this goes to 0. If this goes to 0, this whole term goes to 0, and we're left with just this as the best case model for the data that we have. And recall, this is an interesting example because everything goes back to the correlation coefficient. The correlation coefficient was weak. It was a small value, so it was showing a weak relationship between the variables. It was insignificant, so technically it was just 0. And that translated into a model where the model did not really predict a significant portion of the variation in the response variable. And because it didn't do that, even the hypothesis test for beta 1 turns out to be insignificant. So just as we did the hypothesis test for beta 1 parameter, we can also calculate a confidence interval. The Python example here also printed the confidence interval for beta 1 estimate. The lower limit is negative 0.016. The upper limit is 0.469. That is your confidence interval. Now, interestingly, you'll notice that in the 95% confidence interval, the value of 0 turns out to be within this interval, right? Because you have a negative 0.016 as the lower limit, and the upper limit is 0.469. So 0 is contained in the interval. When that happens, you will generally be not rejecting the null hypothesis that beta 1 is equal to 0, because beta 1 being 0 is contained in this confidence interval. Next, we will study the analysis of variance f-test. Just like we have the hypothesis test for testing the slope parameter for the independent variable, we also have an f-test that tests the overall model. The f-test is given as here. The null hypothesis will be that beta 1 equals 0, and the alternative hypothesis will be that beta 1 is not equal to 0. So just like we had the t-test where we tested the beta 1 parameter. In the case of f-test, when we go into the next 2 weeks and we study multiple regression, you will notice that the f-test will be slightly different because in multiple regression, we can have more than one independent variable. So we can use 4 independent variables or 5 independent variables to predict the dependent variable. And when we have more than one independent variable, then the alternative hypothesis will be slightly different. It will be that at least one of those beta, either beta 1, beta 2, beta 3, beta 4, in the case of 4 independent variable, at least one of them is not equal to 0. The test statistic for F test is the F value that is based on the F distribution. And again, you'll get your p-value. Once you have the p-value, you'll compare it to the alpha, that is typically 0.05. If the p-value is less than alpha, you reject the null hypothesis. And if the p-value is greater than alpha, you do not reject the null hypothesis. Going back to the example here, we notice that the F statistic is printed in the output, and the probability of the F statistic is also printed, which is 0.0668. So what that tells us is that we cannot reject the null hypothesis, and the null hypothesis was that beta 1 equals 0. So the overall model is also not significant. We now move on to the discussion for the week, that is on simple linear regression. And so in this discussion, you will apply the statistical concepts and techniques covered in this week's reading about correlation coefficient and simple linear regression. A car rental company wants to evaluate the premise that heavier cars are less fuel efficient than lighter cars. In other words, the company expects that fuel efficiency, that is measured as miles per gallon, and weight of the car, measured in thousands of pounds, are correlated. And what that means is when we say that they're correlated, that we mean that there is a relationship between the two, and so we expect the correlation coefficient to be sufficiently higher. Performing this analysis will help the company optimize its business model and charge its customers appropriately. In this discussion, you will work with the car's dataset that includes two variables: miles per gallon, this is coded as MPG in the dataset, and weight of the car, that is coded as WT in the dataset. Again, this dataset is unique to you, so your answers will be unique as well. So each student will have a different answer than you. So here's step 1 in the Python script. This step will generate the dataset for you. So we will just run this step, and it will print the first 5 observations. So you'll see that we're only looking at the MPG and the WT variable. So these two variables here. The next step is to create a scatter plot of miles per gallon against weight. So let's look at this plot.
In this particular plot, you can see that we have a negative correlation between the two variables, and you can also put into practice what Professor Kadri explained before. What are we looking for in the relationship between the two variables? You see that as the weight increases, the miles per gallon are going to decrease. So in this case, we have a negative correlation. Secondly, if you were to draw a straight line between these data points, you can get a feel for what are the size of the errors, how far away they are from a straight line between the points, and that will give you a feel for how strong the correlation is. That is what we're looking for with a scatter plot. Is there really graphically a true relationship between the two variables, and to what extent? What is the nature of the relationship? How much are the errors from the straight line?
So this answers the first question. The question was, you created a scatter plot of miles per gallon against weight. Check to make sure it was included in your attachment. Does the graph show any trend? If yes, is the trend what you expected? Why or why not? The third step is where we calculate the correlation coefficient. So in step 2, we saw that we do have a relationship between miles per gallon and the weight of the car. Now we want to get a quantitative measure for that relationship. So therefore we will print the correlation coefficient. So let's print that. So you'll notice that it prints out a correlation coefficient matrix. This matrix, in the case of just two variables, is quite simple. You just look at the value for miles per gallon in the row and WT in the column. That value is negative 0.86. You can do it the other way as well, and it will be the same value. This matrix is particularly useful when you have to calculate the correlation coefficients for many variables. It's easy to just look at X and Y interaction and get the value. So in this case, we see that the value is negative 0.867. So two observations here. First of all, it's negative, just like Professor Wan said, that the plot here represented a negative correlation or negative relationship, where if the weight of the car increases, the miles per gallon decrease. That's what we expect. But this is an example of a negative correlation where one variable increases, the other decreases. This is why this sign is negative. And then the other is the measure itself. It's negative 0.86. And if we recall, this points to a strong negative correlation. So this answers the second question. What is the coefficient of correlation between miles per gallon and weight? What is the sign of the correlation coefficient? Does the correlation coefficient indicate a strong, weak, or no correlation between the two variables? How do you know? In the next step, we will run a simple linear regression model to predict miles per gallon using weight of the car. So now that we have seen graphically as well as by calculating the correlation coefficient that there is indeed a relationship between miles per gallon and weight of the car. So now we want to be able to create a regression model for this relationship. So again, we use the OLS method in statsmodels.formula.api submodule. The model is coded as MPG tilde WT, meaning that MPG is the dependent variable and WT is the independent variable. Again, we get the fit for that model and then we print out the summary. So let's run this step. Here's the summary, and you'll notice that this time the R squared is 0.752. That's 75.2%. We note that the F statistic is 84.8, and the probability for F statistic is 5.75 e to the power negative 10. This is the exponent. This is essentially just 0. So the p-value is 0. And when the p-value is 0, we reject the null hypothesis. And we note that in the case of the F statistic, the null hypothesis was that beta 1 parameter is equal to 0. We reject that, meaning that beta 1 is not equal to 0. And in this case, therefore, the model is significant. So what is the model equation? Well, we note that the intercept given is 37.1877, and the weight, the coefficient for the weight variable is negative 5.3079. That is the slope as well. So we can now write the equation, and the equation is simply just MPG equals 37.1877 minus 5.3079 times WT, weight of the car. And we note here that the t test for beta 1 parameter is negative 9.209 for the test statistic and 0.0 for the p-value. So again, the p-value is 0. We reject the null hypothesis that beta 1 equals 0, and we say that again, the model is turning out to be significant. And in this case, if you note, the 95% confidence interval is negative 6.48 and negative 4.12. note that 0 is not included in this interval. If 0 was included, that would mean that the estimate for beta 1 could be 0, but in this case it's not included, and so again it points to a significant model.
And in this case, you can tell the management of the firm that they can use this model to determine the rental price for the car, because the prediction is quite accurate. You have a strong correlation and a good predictive model.
And so now this answers question 3 and 4. Write the simple linear regression equation. How might the car rental company use this model? And the last question, which is, what is the slope coefficient? The slope coefficient, again, is the coefficient for WT. Is this coefficient significant at 5%? We just covered this. For your follow-up posts to other students, you have to answer these two questions. How do their plots and correlation coefficients compare with yours? And would you recommend this model to the car rental company? Why or why not? So this concludes topic for week 5, which is simple linear regression. And we will return next week for module 6.